Good morning, everyone, and welcome back. I hope you guys had a great weekend. I apologize for not being able to give this lesson live, but if you have any questions for me later, let me know. You can always send me an email, or you can ask me the question later on the next time we meet. So today we're going to be finishing up chapter 17, which is all about acids and bases. So in the past two lessons, you've learned all of the following except for equilibrium and weak bases. You learned the general properties of acids and bases. You learned that there are three different definitions of acids and bases. The first one is the Arrhenius definition. The second one is Bronsted-Lowry definition. And the third one is the Lewis acid and base definition. But we're only focusing on the first two here. So you learned that an Arrhenius definition, an acid is anything that releases a hydrogen ion. And an Arrhenius base is anything that releases a hydroxide ion in solution. On the other hand, a Bronsted-Lowry acid is any compound that can donate a proton or a hydrogen ion, whereas a Bronsted-Lowry base is any compound that can accept a proton or a hydrogen ion. And then you also learn that there are ways to identify whether we have a strong acid or a weak acid, or a weak base or a strong base. And one way to do that is to look at the acid and base ionization constant, Ka versus Kb. So Ka is the equilibrium constant for an acid, Kb is the equilibrium constant for a base. And so the higher the Ka or Kb value, the stronger the acid or the base. You can also look at the strength of acids and bases by looking at the pH and pOH. So if the pH is less than 7, then you know that it's going to be an acidic solution. If the pH is greater than 7, then you know that it's going to be a basic solution. And in terms of pOH, if the pOH is less than 7, then you know that it's going to be a basic solution. And if the pOH is greater than 7, then you know that it's going to be an acidic solution. So it's kind of the reverse of the pH. If the pH and pOH are equivalent to 7, then you know that we have a neutral solution. We can also classify the strength of acids and bases by simply looking at the pKa values and the pKb values. So if you remember that the Ka and the Kb values are inversely proportional to the pKa and pKb. So if the Ka is high, then the pKa is low. Same thing with pKb and Kb. You can also look at percent ionization to tell whether we have a weak acid or a strong acid. So if the percent ionization is high, then you know that we have a strong acid. And then we also looked at how to calculate the pH of a mixture of acids. We looked at how to determine the pH of a mixture of a strong acid and a weak acid, as well as a mixture of two weak acids. And finally, today we're going to look at equilibrium and weak bases. So strong bases are strong electrolytes. So that means that if you were to dissolve a strong base in aqueous solutions, they will dissociate completely, 100%, into ions. So for example, if we have ionic bases like sodium hydroxide, these are known as a strong base and also a strong electrolyte. And so they will dissociate completely into ions, into hydroxide and sodium ions. And so if we have 1 molar solution of sodium hydroxide, this will dissociate into 1 molar of sodium ions and 1 molar of the hydroxide ions. Some strong bases can have multiple hydroxide ions. And so, for example, if we have strontium hydroxide, you can see that in the chemical formula, for every 1 mole of this compound, 1 mole of strontium will dissociate into ions, and 2 moles of hydroxide ions will be in solution. And so in that case, if we have 1 molar solution of the compound, 2 molar concentration of hydroxide will be present, and 1 molar of the strontium ions will be present. And here is a table showing you some of the most common strong bases. We have lithium hydroxide, LiOH, sodium hydroxide, potassium hydroxide, and some hydroxides containing multiple hydroxide ions, such as strontium hydroxide, calcium hydroxide, and barium hydroxide. So make sure that you remember these strong bases shown here. Weak bases, on the other hand, are considered weak electrolytes because they don't dissociate completely in aqueous solutions. So just like weak acids, only about 1% of them get ionized in water. And so that means that the concentration of the hydroxide ion in solution is going to be a lot less compared to the concentration of the weak base. So for instance, if we have 1 molar ammonia solution, less than 1 molar of hydroxide will be present in solution. So finding the pH of a weak base is actually similar to how you would find the pH of a weak acid. So you're going to prepare your ice table and then determine the initial concentrations of the acids or the bases, and then determine the change as well as the equilibrium concentrations. So the strength of a base can also be determined by calculating the equilibrium constant when the base reacts with water. So you can see here the chemical reaction equation of a base reacting with water, which generates a hydroxide ion and a conjugate acid. So the equilibrium constant is called the base ionization constant, which has the symbol Kb, and the Kb expression is shown here. So we can calculate Kb by simply multiplying the concentration of the products raised to their coefficients divided by the concentration of the reactant raised to its coefficient. So just like the Ka for the acids, the larger the Kb value, the stronger the base. So here's the table that shows you some of the most common weak bases. So we have carbonate ion, methylamine, ethylamine, all the way down to pyridine and aniline. We also have the Kb values shown here. So remember that the higher the Kb value, the stronger the base. And the lower the Kb value, the weaker the base. So in that case, carbonate ion here has the highest Kb value, and so it will have, this would be the strongest base here on the list. On the other hand, aniline has the lowest Kb value, so this is going to be the weakest base here on the list. And here in the middle, we have the ionization reactions. So you can see how the weak base is reacting with water, which in this case is acting as an acid. And in this chemical reaction, it will generate a conjugate acid and a conjugate base. So here we have a class of organic compounds known as amines. And amines are considered Bronsted-Lowry bases because they contain at least a lone pair of electrons. So you can see that all of these compounds contain nitrogen atoms, and these nitrogens contain a lone pair of electrons, and so they have basic properties. So we have ammonia, methylamine, and pyridine. So these are all examples of Bronsted-Lowry bases. So here's a quick review regarding Bronsted-Lowry acids and bases. Determine the conjugate acid-base pairs. So for the first one here, we have an ammonia reacting with water. So this reaction releases a hydroxide ion and an ammonium ion. So you can see that the ammonia here, NH3, is the one that accepted a hydrogen ion. So that means that water is acting as an acid and ammonia is acting as the base. And so in that case, we have base, acid, conjugate acid, and then the conjugate base. And for the second one here, we have the reaction between methylamine and water. And analyzing the products here, we have hydroxide ion and the methylammonium ion, in which the positive charge is on the nitrogen atom. So you can see that water is the one that's acting as an acid because it donated a hydrogen to the methylamine, as shown here. And so in that case, we have the acid, the base, the conjugate acid, and then the conjugate base. So here's an example. Determine the hydroxide concentration and pH in each solution. So we have 0.225 molar potassium hydroxide and 0.0015 molar strontium hydroxide. So the first thing that you want to do here is to identify the strength of the base. Do we have a strong base or a weak base? So you can see that we have potassium hydroxide and strontium hydroxide, and they're both examples of a strong base. And so in that case, both bases will dissociate 100% in aqueous solution. And so the hydroxide concentration is equivalent to the concentration of the base itself. So for the first one here, for every 1 mole of potassium hydroxide, it will generate 1 mole of potassium and 1 mole of the hydroxide ion. So if we have 0.225 molar solution of KOH, then it will generate 0.225 molar potassium solution and 0.225 molar hydroxide solution. So again, the concentration of the hydroxide is going to be 0.225, which is essentially the same as the concentration of the base itself. And so when calculating the pH of the solution, first thing you want to do is calculate the pOH, and this is essentially the negative log of the concentration. So here we get 0.65. And so to calculate the pH of the solution, all you have to do is subtract the pOH from 14. So remember that pH plus pOH gives us 14. And so in that case, to calculate the pH of the solution, all you have to do is subtract pOH from 14. So we get 13.4 for the pH. And for the second part here, we have 0.0015 molar strontium hydroxide. And so for every 1 molar of strontium hydroxide, this will actually generate 2 molar of the hydroxide ion. And so in that case, all you have to do is double this concentration here for the concentration of the hydroxide. And so now we can do the same thing. We can calculate the pOH first. So pOH equals the negative log of the concentration of the hydroxide, which is 0.0030. And so we get 2.52. And to calculate the pH, all you have to do is subtract 2.52 from 14. And we get the pH, which is 11.48. And that's it. And here's another example. Find the hydroxide concentration and the pH of a 0.100 molar ammonium solution. And the Kb value here is 1.76 times 10 to the negative 5. So here you can see that we have a weak base. And so we're going to have to set up our ice table and then come up with the Kb expression. So the very first thing that you want to do here is to set up your ice table as well as the chemical reaction equation. So you can see that reacting the ammonia with water will generate ammonium ion and the hydroxide ion. And then we're going to set up our ice table here. So the reactant is ammonia, and then the products are the ammonium ion and the hydroxide ion. So you can see that initially the concentration is 0.1 molar for the ammonia solution. So we're going to put 0.1 here. And then for the products, it's going to be 0 for both. And for the change here, since we have the products starting at 0, the change will be positive for both products and then negative for the reactant. So we're going to have a negative X here and then positive X for both products. And then for the equilibrium here, we can solve the equilibrium in terms of X. So we have 0.100 minus X. And then for the products, we have X and X. And then now we can set up our Kb expression based on the chemical reaction equation here. So the Kb expression is going to be the concentration of the products raised to their coefficients divided by the concentration of the reactant raised to its coefficient. And again, liquids and solids are omitted in the equilibrium constant expressions. So now we're going to set up our Kb expression here. So Kb is equivalent to the concentration of the products, which in this case is hydroxide ion and the ammonium ion, raised to their coefficients, divided by the concentration of the ammonia. And so here we know what the Kb value is. It's 1.76 times 10 to the negative 5. So we can go ahead and substitute it for Kb here in the equation. So 1.75 times 10 to the negative 5. And then this is equivalent to the concentration of the hydroxide in terms of X times the concentration of the ammonium ion in terms of X divided by the concentration of ammonia, which is 0.1 minus X. So we have X squared divided by 0.100 minus X. So basically we have X times X, which is equal to x squared, divided by 0.1 minus x. And let this equal to Kb, which is 1.75 times 10 to the negative 5. And so you can see that the value of Kb is less than 10 to the negative 3. And so that means that we can use the approximation method. So we can assume that x is mole here. And so now we have 1.75 times 10 to the negative 5 equals x squared divided by 0.1. And so now we can solve for x. And to simplify the math, we can take the square root of both sides. And then isolate for x. So in this case, we have x equals 0.0013. So x here is going to be the concentration of the hydroxide ion as well as the concentration of the ammonium ion. And so since we use an approximation method here, we have to validate this value. So all you have to do is divide this by 0.1 multiplied by 100%. So we're going to validate this. So we have 0.0013 divided by 0.100 times 100%. And if we get less than 5%, then we have a valid approximation. And so what we have here is 1.32%, which is less than 5%. So this is a valid approximation. So now the question here is calculate the pH or find the concentration. And so in this case, this is the concentration. We can go ahead and circle this. So this is the concentration of the hydroxide ion. And so now we have to calculate the pH of the solution. So what we can do is we can calculate the pOH and then solve for the pH. So the pOH is equal to the negative log of this number, which is 0.0013. And we get 2.88. And to get the pH, all you have to do is subtract 2.88 from 14. So 14 minus 2.88, and we get 11.1. So the pH of the solution is going to be 11.12. And that's it. So a lot of acid-base reactions result in the formation of salts, and soluble salts form ions in solution. So let's take a look at some of the properties of these salts and ions in solution. So cation of a strong base and the anion of a strong acid do not ionize water. So that means that it doesn't really affect the pH of the solution. However, the cation of a strong base and anion of a weak acid will ionize water, and this will affect the pH of the solution. So here's an example. We have a salt here. This is sodium bicarbonate. And sodium bicarbonate in water will result in a basic solution. And the reason why is sodium is a cation of a strong base, such as sodium hydroxide, whereas a bicarbonate is the conjugate base of the weak acid, which is carbonic acid. And so again, it says here that the cation of a strong base and the anion of a weak acid will ionize water. And again, the weak acid here is the carbonic acid. So the bicarbonate ion is basically the anion of the weak acid, which in this case is the carbonic acid. So anions tend to form basic or neutral solutions, whereas cations tend to form acidic or neutral solutions. So every anion can be thought of as the conjugate base of an acid, because if an acid is ionized in water, this generates an anion, which is essentially a conjugate base. And so every anion can potentially be a base. Here's an example. So if an anion is in water, the anion can act as a base and the water as the acid, and this generates a conjugate base and a conjugate acid. And one thing that you should remember is that the weaker the acid, the stronger the conjugate base. But it doesn't necessarily mean that the conjugate base is a strong base. And the anion of a strong acid will have a neutral pH. So an example here is chloride ion, which is the anion of a strong acid, which is hydrochloric acid. So if you were to put a chloride ion in water, the solution is going to have a neutral pH. And the reason why is because the chloride ion isn't strong enough of a base to be able to remove a proton or a hydrogen from water. And so this reaction right here will never happen. The chloride ion will remain a chloride ion in water. And for the last one here, an anion that is the conjugate base of a weak acid is itself a weak base. So what that means is that the conjugate base of a weak acid will actually generate a little bit of hydroxide ion. And so it'll turn the solution slightly basic. An example here is a fluoride ion. And a fluoride ion is the conjugate base of a weak acid, which is hydrofluoric acid. And so this fluoride ion will be able to deprotonate or abstract one of the hydrogen atoms of a water molecule, which then generates some hydroxide ions. And so again, it'll turn the solution slightly basic. So here's the table that shows you the relative strength of conjugate acid base pairs. On the left, we have the acids, and on the right, we have the bases. And the acid strength increases from bottom to top, and for the bases, the strength increases from top to bottom. And so it says over here that the weaker the acid, the stronger the conjugate base. So let's take a look at two examples here of acids and their conjugate bases. So we have hydrofluoric acid and acetic acid. So hydrofluoric acid has a conjugate base, which is fluoride ion. And the acetic acid has the conjugate base acetate ion. So you can see that the hydrofluoric acid is the stronger acid, but its conjugate base is the weaker base. So again, acetic acid is the weaker acid here, and so it's going to have a stronger conjugate base. So here's an example. Classify each anion as a weak base or pH neutral. So for the first one here, we have a nitrate ion. And nitrate ion is the conjugate base of a strong acid, which is nitric acid. So this is a strong acid. And since the nitrate ion is an anion of a strong acid, the pH of the solution is going to be neutral. And for the second one here, we have a nitrite ion. And so we know that this is a conjugate base of a weak acid. So this is a conjugate base of a weak acid. And so based on the previous slide, the conjugate base of a weak acid is itself a weak base. And so because this is acting as a weak base, it's strong enough to be able to deprotonate a water molecule. So meaning you'll be able to abstract a hydrogen from a water molecule. And so this is going to be a weak base. And for the last one here, we have an acetate ion. And acetate ion is the conjugate base of a weak acid, which is acetic acid. So again, this is the conjugate base of a weak acid. And the weak acid is acetic acid. And so in that case, this acetate ion is a weak base. And here's another example. Find the pH of a 0.100 molar sodium formate solution. The salt completely dissociates into sodium ion and formate ion, and the sodium ion has no acid or base properties. And the Ka value is also given here. It's 1.8 times 10 to the negative fourth power. So the first thing that you should do here is to set up the ice table and the chemical reaction equation. So we have the formate ion that's reacting with water to form the formic acid and the hydroxide ion. So again, we have the conjugate base reacting with water as the acid, and this generates a hydroxide ion, the conjugate base, and the formic acid, which is the conjugate acid. And again, we're given the Ka value here, which is 1.8 times 10 to the negative fourth power. And so here we're given the initial concentration of the salt, sodium formate, and that's 0.100. So we're going to put 0.100 here, and then 0 for the acetic acid and the hydroxide ion. And then for the change, since we have 0 concentration for the products, these products will receive the positive change, and then the reactant the negative change. So we're going to put negative X here, and then positive X for both products. And then now we're going to solve for the equilibrium in terms of X. And in order to calculate the concentration of hydroxide ion in terms of X, what we need here is the Kb value, not the Ka. And so we can calculate the Kb value from Ka, knowing that Ka times Kb yields Kw. And you learned that the ion product constant for water is equivalent to 1.0 times 10 to the negative 14 power. So if we know the concentration, or if we know the Ka value, we can calculate for Kb. So in that case, we have Kb equals Kw divided by Ka. And so that's 1.0 times 10 to the negative 14 divided by the Ka, which is 1.8 times 10 to the negative 4. And so we can calculate for Kb here. And the Kb value is 5.56 times 10 to the negative 11th. All right, so now we can set up our Kb value here, or our Kb expression. So Kb is equivalent to the concentration of the hydroxide ion times the concentration of the formic acid divided by the concentration of the formate ion. All right, so let's create some space here. And so we have 5.56 times 10 to the negative 11th, and this is equivalent to x squared divided by 0.1 minus x. And so here we can use the approximation method because again the Ka or the Kb value is less than 10 to the negative 3. And so we're going to treat x as a small number. And then we can simplify this by taking the square root of both sides and then solve for x. And so x here is equal to 2.36 times 10 to the negative 6. So this is the concentration of the hydroxide ion and also the concentration of the acid, formic acid. And to solve for the pH, first we have to solve for the pOH. So again, the pOH is the negative log of the concentration of the hydroxide, which in this case is this number right here, 2.36 times 10 to the negative 6. So we'll take the negative log of that number. And this gives us 5.63. So the pOH is 5.63, and the pH of the solution is going to be 14 minus 5.63. And the answer is 8.37. So now let's take a look at cations as weak acids. So remember that the stronger the base, the weaker the conjugate acid. And you can take a look at the table that I showed you earlier regarding the relative strength of conjugate acid-base pairs. And here's 3 other things that you should remember regarding cations. The first one is a cation, that is the counter ion of a strong base, is considered pH neutral. So these cations are sodium ion, potassium ion, calcium ion, lithium ions, strontium ions. These are all counter ions of a strong base. Okay, so sodium hydroxide, for example, is a strong base. Potassium hydroxide, lithium hydroxide, calcium hydroxide, and so on and so forth. So these are all strong bases. And so the cations of these strong bases will be pH neutral. And the second one here is a cation that is the conjugate acid of a weak base is considered weakly acidic. So these cations are ammonia, for example. This is actually a perfect example. Ammonium ion is a cation, which is the conjugate acid of ammonia, NH3. And so ammonium ion is considered weakly acidic because it is the conjugate acid. So if you look at it in reverse direction, you can see that ammonium will be donating a hydrogen ion. So it's acting as a weak acid. And finally, a cation that is a small, highly charged metal ion forms weakly acidic solution. And so the pH is going to be less than 7. And so when you look at aluminum ions, iron ions, aluminum-containing compounds like aluminum hexahydrate, for example, if this dissociates in water, it will actually release hydronium ions, which is considered weakly acidic. In terms of metal ions, the smaller and more highly charged the cation, the more acidic its behavior. So here's an example. Classify each cation as a weak acid or pH neutral. So for the first one here, we have a conjugate acid of a weak base. So we know that this is a cation, and this cation is a conjugate acid of a weak base. And so because this is a conjugate acid, we're going to have a weakly acidic solution. So we have a conjugate acid, and so the solution is going to be weakly acidic. And so therefore this is a weak acid. And for the second one here, we have a calcium ion, and this is a counter ion of a strong base. Counter ion of a strong base. Strong base such as calcium hydroxide. And so in that case, this will generate a neutral pH. All right. And for the last one here, we have chromium with a positive 3 charge. So this is a highly charged metal ion. And so this is going to produce a weakly acidic solution. So this is weakly acidic. Salt solutions can also be classified as either acidic, basic, or neutral, depending on the strength of the acids and bases in the acid-base reaction. So how do we classify salt solutions as acidic, basic, or neutral? If the salt cation is the counter ion of a strong base, and the anion is the conjugate base of a strong acid, then it will form a neutral solution. So in other words, any salts formed from a strong acid and strong base combination will result in a neutral solution. So for example, here we have sodium chloride, calcium nitrate, and potassium bromide. These salt solutions will have a neutral pH. And so if you look at the chemical formula of sodium chloride here, sodium is the cation or the counter ion of a strong base, which is sodium hydroxide. The chloride ion is the anion that's generated from the ionization of hydrochloric acid, which is a strong acid. Here we have calcium nitrate. So calcium is a counterion of a strong base, calcium hydroxide, and nitrate is the conjugate base of a strong acid, nitric acid. And here we have potassium bromide. Potassium, again, is a counterion of potassium hydroxide, a strong base, and the bromide ion is the conjugate base of hydrobromic acid, which is a strong acid. And if the salt cation is the counterion of a strong base and the anion is the conjugate base of a weak acid, then it will form a basic solution. So in other words, any salts resulting from the combination of a weak acid and a strong base will result in formation of a basic solution. So the pH is going to be greater than 7. So here are some examples. We have sodium fluoride, calcium acetate, and potassium nitrite. And so strong beats the weak. And so whenever you combine a weak acid with a strong base, it will result in a basic solution. So again, sodium is a counterion of a strong base. Fluoride ion is the conjugate base of a weak acid, which is hydrofluoric acid. Calcium is a counterion of calcium hydroxide, which is a strong base. And acetate ion is the conjugate base of a weak acid, which is acetic acid. And here we have potassium, a counterion of potassium hydroxide, and nitrite is the conjugate base of nitrous acid, which is a weak acid. And if the salt cation is the conjugate acid of a weak base, and the anion is the conjugate base of a strong acid, then it will form an acidic solution. So in other words, any salts resulting from a combination of a strong acid and a weak base will result in the formation of an acidic solution. So the pH is going to be less than 7. So a combination of a strong acid and a weak base, you would have a lot more hydronium ion compared to hydroxide ion. So again, you can also think of it in terms of the concentration of the hydronium ion generated or the concentration of the hydroxide that's generated. So in a strong acid, weak base combination, you'll have a lot more hydronium ion than hydroxide ion. And so here's an example. We have an ammonium chloride. Ammonium is the cation, which is a conjugate acid of a weak base. Ammonia is a weak base, NH3. And chloride ion is the conjugate acid, or the conjugate base of a strong acid, which is hydrochloric acid. And if the salt cation is a highly charged metal ion, and the anion is the conjugate base of a strong acid, then it will form an acidic solution. So the nitrate ion here is the conjugate base of a strong acid, which is nitric acid. And so this will form an acidic solution. And finally, the pH of a salt solution resulting from a combination of a weak acid and a weak base will depend on the Ka and Kb values. So if the Ka is greater than the Kb value, then we're going to have an acidic solution. Otherwise, it's going to be a basic solution. So here's an example. Determine if the solution formed by each salt is acidic, basic, or neutral. So for the first one here, we have strontium chloride. And strontium has a positive 2 charge, which is a counter ion of a strong base. And the chloride ion is the conjugate base of a strong acid. And so since we have a strong base and a strong acid combination, we're going to have a neutral pH. And for the second one here, we have aluminum bromide. And bromide here, so the bromide here is the conjugate base of a strong acid. And the aluminum ion has a highly charged metal ion, and it's going to generate a weakly acidic solution. But because we have a strong acid mixed with a weak acid, then we're going to have an acidic solution. And for part C, we have CH3, NH3, NO3. And so with this one, we have, again, a salt. We have CH3, NH3 with a positive charge, and then the nitrate ion, NO3 minus. And so you can see that the nitrate ion comes from nitric acid, so which is a strong acid. And then this methyl ammonium ion here comes from a weak base. And so we have the conjugate acid of a weak base, and then the conjugate base of a strong acid. And so this solution, this salt solution, is going to be acidic in nature. And for part D here, we have sodium ion. We have a sodium formate, CHO2. And so the sodium ion here comes from sodium hydroxide, which is a strong base. And the formate ion here comes from a weak acid. And so this is the conjugate base of a weak acid. And so therefore, we're going to have a higher concentration of the hydroxide compared to the hydronium ion. And so we're going to have a basic solution. And for the last one here, we have ammonium fluoride. So we have NH4 plus and a fluoride ion. And the ammonium ion is the conjugate acid of a weak base, which is ammonia, NH3. And the fluoride ion is the conjugate base of a weak acid, which is hydrofluoric acid. And so since they're both weak base and weak acid, we're going to have to compare them in terms of their Ka and Kb values. So if the Ka value is greater than the Kb value, then we're going to have an acidic solution. Otherwise, we're going to have a basic solution. And so how do we find the Ka and Kb? Well, since we have a conjugate acid here, we're going to need its Ka value. And since we have a conjugate base here, we're going to need its Kb value. So how do we determine the Ka and Kb values? Well, we're going to have to look at the Kb value of ammonia and then solve for the Ka. So the Kb value of ammonia here is 1.76 times 10 to the negative 5. And so in order to solve for the Ka of ammonium ion, the conjugate acid, we're going to have to use this equation Kw equals Ka times Kb. And then all you have to do now is isolate Ka, and we know that Kw is equivalent to 1 times 10 to the negative 14. And so we can isolate and solve for Ka. So Ka here is equal to 5.68 times 10 to the negative 10. All right, so this is the Ka value of ammonium ion. And then now we're going to have to find the Kb value of the fluoride ion. But first, we're going to need the Ka value of hydrofluoric acid. This is equivalent to 3.5 times 10 to the negative 4. And then again, we can use this equation right here, Kw equals Ka times Kb, to solve for Kb. All right, so Kb then, again, the Kb here is for the fluoride ion. And this is 2.9 times 10 to the negative 11. And so now we're going to have to compare the value, the Kb value, from the Ka value. And so you can see that the Ka is greater than the Kb value. And so therefore, we're going to have an acidic solution. So this is going to be acidic. Some acids contain multiple ionizable protons, and these are called polyprotic acids. A diprotic acid contains 2 ionizable protons. An example is sulfuric acid, H2SO4. A triprotic acid contains 3 ionizable protons, and a perfect example is phosphoric acid, H3PO4. And since polyprotic acids ionize in multiple steps, each hydrogen ion has a separate Ka value. An example that we have here is sulfurous acid. Its first ionization has a Ka value of 1.6 times 10 to the negative 2. And for the second ionization, it has a Ka value of 6.4 times 10 to the negative 8. And the first ionization constant is usually greater than the second, and the second is greater than the third. And here's a table that shows you a list of the most common polyprotic acids and their ionization constants. So we have sulfuric acid, oxalic acid, sulfurous acid, all the way down to carbonic acid. And you can see that they all have multiple Ka values. For example, sulfuric acid has a second ionization constant, which is 1.2 times 10 to the negative 2. Oxalic acid has 2 ionization constants. The first one is 6.0 times 10 to the negative 2, and then the second ionization constant is 6.1 times 10 to the negative 5. And so you can see the trend in ionization constants. The first is usually greater than the second, and then the second is usually greater than the third. And here's one final example. Find the pH of a 0.0100 molar sulfuric acid solution. So we're provided 2 different equations here. One is for the first ionization, and then the second one is the second ionization, and it gives us a Ka value, which is 0.012. So whenever you're determining the pH of a diprotic acid or a polyprotic acid, what you need to do is to determine the concentration of the hydronium ion for the second ionization, because we have a Ka value. So we can use a Ka value to determine the concentration of the hydronium ion. And so we're going to focus on the second ionization here. And so the first thing that you want to do is set up the ice table as shown here. So we have the hydrogen sulfate, the hydronium ion, and the sulfate ion concentration. And so here's our ice table. The initial concentration of the hydrogen sulfate is equivalent to the concentration of the acid itself, because the sulfuric acid will ionize completely in water. And so the concentration of sulfuric acid is equivalent to the concentration of the hydronium ion and the concentration of the hydrogen sulfate. And so for the second ionization here, the concentration is going to be 0.01. And for the hydronium ion, it's the same thing. It's going to be 0.01 as well. But for the sulfate ion, the initial concentration is going to be 0. And then we're going to set up our change. And since we have 0 for the sulfate ion, the products will receive the positive X. And then the hydrogen sulfate, the reactant, will receive the negative X. And now we can solve for the equilibrium as a function of X. So for the hydrogen sulfate, it's going to be 0.01 minus X. And then over here we have 0.01 plus X. And then for the sulfate ion, plus X. Alright, so now the next step here is to set up our Ka expression for the second ionization here. And so this is our expression, Ka expression, so that would be concentration of the hydronium raised to the first to its coefficient, times the concentration of the sulfate ion raised to its coefficient, divided by the concentration of the hydrogen sulfate. And we know that Ka value, the Ka2 here, is equal to 0.012. Alright, so now we substitute the equilibrium equations onto the expression. And so we have 0.012 equals X times 0.01 plus X divided by 0.01 minus X. And since the Ka value is greater than 10 to the negative 3, we can't use the approximation method here. So we're going to have to use the long method, which is the quadratic formula. And so we can go ahead and simplify the math here, combine like terms, and we get this quadratic equation, which is x squared plus 0.022x minus 0.00012, and set that equal to 0. And then we now have our a, b, and c values here. So a equals 1, b equals 0.022, and C is going to be negative 0.00012. And now we can use the quadratic formula. And all you have to do now is plug in the values for A, B, and C. So we have negative 0.022 for negative B, plus minus the square root of this function here. And divide all of that by 2A, which is basically 2 times 1. Because again, our A value here is equivalent to 1. And so what we get is 0.00452 molar for the X value. So the concentration of the sulfate ion is 0.00452. And then for the hydronium ion, we would add 0.01 to 0.00452. And so when we add them together, we get this concentration for the hydronium ion, which is equal to 0.0145. And so the question here is find the pH of the solution. And so all you have to do now is take the negative log of the concentration of the hydronium ion. And so negative log of the hydronium ion concentration will give us 1.84 for the pH.